Okay, so one question is on question 2A, part B. Um, that's from the last year midterms that I shared. So I'm going to share the screen for the midterms last year. So 2B, let's go to, um, I think you mean this one, because that's where it says KR equal to 0. If you mean that one,
No, sorry.
oh, this one.
Yeah, that one.
Okay,
2B.
okay, got it. All right, so K, see, there are two terms here. One is KR, KR means K reactions. Another is KS. So K sorption, that means how much is adsorbed on the solid. So there are two type of reaction that can happen that makes the contaminants move go away from water. Okay, so one is reaction; it can react, decompose to something else. So that's K reaction. That's saying 0.01 per day. That's the reaction that happened. The second one, it says Ks equal to 0, and it says a solid water partition coefficient, Ks equal to 0. And it says exactly what that means. It means no sorption. So that's the same as Kd that you see in the retardation factor, exact same number. People write Kd, Ks, they interchangeably write that number. What that means is, it means concentration. When you put a solid in a contaminated water, some of the contaminants will adsorb on the solid. So the Ks determine how much contaminants will adsorb. So that's basically a ratio of concentration of contaminant adsorb divided by concentration of contaminants remain in the water after adsorption. So that's what I wrote here. Um, Somewhere in the solution. So I that's why I explained this one when I wrote it. So here, okay, adsorption coefficient is the ratio of concentration of sorbed contaminant on solid and the remaining dissolved contaminant in water. So that's concentrations sorbed divided by concentration remain in water. And so concentration of contaminant sorbed is basically mass of contaminant divided by mass of the material where it is sorbed, which is in this case suspended solid. Same thing, concentration of contaminant in water is mass of pollutant in water divided by volume of water. So that's basically this. And this is what we wrote for KD. Okay, that's absorption is the process here.
Gotcha. That makes sense. Thank you.
Yeah, check this one. So because I explained that very different step and I go from very basic things to and then keep adding one term extra and explain each step. And this will be able to help you. And it's the same thing. You can do the next questions. I didn't do it because the same process.
Sorry, could you explain again what capital MSS means again? Is that molar mass of the suspended solid?
Okay, okay. Sorry, I should have written all this. So think of concentration. Concentration of contaminant in solid. Concentration means pollutant somewhere divided by the media itself. Okay. So here the concentration is a mass ratio. So mass of pollutant divided by mass of the stop where pollutants are adsorbed to. So here the stops is suspended solid. So 1 gram or whatever suspended solid you have in that water.
Yeah.
Yeah, molar mass and all these things. So many times you write different notation, so it's very easy to get confused. So think of the term before that. That kind of maybe able to. Uh, I should have written somewhere, but let's see the notation. Any other notation that can be confusing? So S is basically fraction solid. Okay, solid is S. Suspended solid means SS. Settled solid, I don't know how to write it. It's still also SS, so I read it settled. That means it's so that way you can see that one. S means amount of solid, suspended solid settled. Okay. Yeah, ask these questions and also, you probably didn't have time to look at it. You can check and ask on campus where. Take a screenshot and say what is this term. I'll just write away right there. So as you see, every term fraction remove, I'll start with what is the definition means. Fraction remove is by sedimentation. So that means amount of suspended solid settle divided amount of suspended solid present in the beginning before settling. So that's the ratio. And then I say, okay, well, suspended solid, what is inside is exactly what is going leaving the system unsettled, because in has to be equal to out. And then I just divide each, for each term I expanded. Okay. And then you will get the equations like this, which is what the previous instructor, they wrote it, but didn't explain it. So that's why it's very difficult to relate to that one. Any question about the midterms, the last year midterms? And I mean, good and bad thing about last year midterms is that because the last year midterms, the same question will not be there, but the question will be similar. At least the concept will be similar. And I would suggest that definitely look at this question. This is also a long question in your homework. Okay, and so this question is there, and this question doesn't change. You have a system which has certain depth. You have also a system with bulk density, porosity, KD, all those given to you, and you are calculating retardation factor or velocity or time. And so these are all same thing, so there is nothing different. So it's the same process. So, I mean, there is no way I can change this question in a different way. So just make sure that this question you know. So this is one question always going to be in the midterms. And settling, as I said, we didn't use Stokes' law here anywhere. We just say that settling velocity. You didn't have to calculate it based on particle size. So normally that's the case in many of the stormwater treatment system, because settling velocity depends on size of particles. And yours, the size of particles are not consistent everywhere. So they just give a ballpark number of how was the settling velocity. So that's why this equation, these questions, you see settling velocity is given. They didn't say about calculate settling velocity based on the particle size, which is Stokes' law. Okay. All right. So there are some other question on the chat window. I'll read it. Would you be able to post the solution set that describe the method in more details? Oh yeah, yeah. These are all posted.
Yeah, I just saw this. Thank you.
Yeah. So you can also see that let me go to um, CCLE, that we can see the same thing in those annotated slide, because whatever annotation I had it in during the class, live class, I changed them and make it more clear and upload them. So you can see those there too. So let's see, I'm going to share the screen for CCLE. So if you go to midterms review annotated, these are things in the class, but after the class I started the process, fraction, sorption, remove. I wrote all the steps so that you can finally find the number. But these are all in the PDF documents or the actual solution for the midterms. I update them. So the reason I want to say that this term here is very different from the last instructor, how that equation was, but the number is ultimately you get the same answer. So there are many ways to get to that point, based on which term you decide to keep, which term you decide to remove. And so anything we discussed today, if I type anything, I'll add to on top of these slides, and I'll update this slide, post it. So any other question?
So I have a question regarding, I believe it's homework 4, where it talks about homework 4, question 5 on the biofilter. So I'm just wondering why we have to divide by porosity, the velocity of water, in order to get the velocity through the pores.
Oh, I see, the Darcy's
ring a bell?
velocity. Why you have to divide Darcy's velocity by porosity?
Mm-hmm.
Okay, so that's a fair point. So Darcy's velocity is not the actual velocity of how water moves. Okay, it is an empirical term, or it doesn't have a physical meaning. Darcy's flow has a meaning. The Q is what is used. So basically, if you dig a hole in a ground and it has water, like groundwater well, how much water will drop into that well is what that Q means. Okay. So this is what you know. But now question is, how fast that water moves inside the pore before it drop into that well is what we are looking for, water velocity. And so Darcy's velocity, calculate Darcy's velocity, assume that water is moving throughout the entire soil. That means there is no solid. It's moving the entire area. If you see this area, KIA, that's the area cross section of entire well. But water doesn't move through the soil. It moves through the pore only, right? So the entire area is not actually used for water, making water move. It's only the fraction of that area which has only the pores. That's where water is coming out. So that's why the real velocity have to be account for that area. So that porosity is the fraction of that area is actually pores. So the real velocity is what is the Darcy's velocity divided by porosity.
Gotcha. Okay. Yeah, that makes sense. Thank you.
Good. Any other question on homework 4? So by the way, homework 4, I would definitely encourage question number 5. You guys have to understand these questions. Okay, that's one question in your midterms. That's used for every single type of green infrastructure, whether it's a green roof, bioretentions, wetland, anywhere. There is a filter. There is these equations. So you got to understand how to use this. And these questions will be more like a short questions, like quiz questions, but with explanation. In quiz, you choose answers. Here, you will not give in any answer. You will say the answer and you explain it. That way, even you have a wrong answer, you still get credits for writing this explanations. But you should be able to answer, because if you did well 90% in quiz, that means you'll do well 90% in the midterms or better, because you have no time constraint here. So any question on this? And I will not ask you to solve this kind of differential equations. At least, not what is not in the homework, not something new type of differential equation to solve. I didn't set a question yet, but I'll say if you okay, so any questions? I can open that. Let's see, homework 2, homework 3. Let's go to the homework 3. In homework 3, as I said, mass balance is integrated to these questions. So this is supposed to be something you should know. Any kind of chemistry questions, you'll have not long question. This will be mostly short conceptual questions. So that means I can only see question number 1 as a long questions, and question number 4 or 5 hydrograph is sometimes I do ask Excel, but because we didn't really go through this hydrograph very well, I'll not ask that one, but I'll give a extra homework on this particular question, because I realize this is something important for your projects, and we cross over it. I'll give you just one extra homework just for this question again, a similar question, so that you can calculate composite hydrograph for a rainfall patterns at a site. That way you could do that for your own projects. And I created the Excel file. I'll do example with the Excel file so that you can do the same thing with another Excel file and a new rainfall. So you learn this process. So this is a very important question actually for this class. But I will not ask this one in the midterms because I didn't really spend time uh, helping you how to do this one. But this is a step. Everything is all set already. Okay. But every question, think of the concept behind it. Every question, even though it's not a, for instance, oxidation, you should know how to calculate oxidation state. You should know how to solve a oxidation reactions, redox reaction, and balance it. So that those are the things that you should know. And these are already you know from CE153, but if you don't, you got to learn how to do it. So I'm just going to go through each question just to say that what's the concept. Settling is basically Stokes' law. This equation you have to understand conceptually. Settling velocity depends on particle size and density difference, and all the viscosity, blah blah blah. But the key critical point here is that it depends on particle size. And settling is the way things remove from the system, and how much it remove you can compare with the overflow rate, all that stuff. That will tell you that will help you decide what's the size of the retention basin should be. And then in the example midterm question, it says that that some of the dissolved pollutant can stick with these particles and settle. And so if they do that happens, then what fraction of the contaminants are removed because particles are settling? That's something I didn't give in the homework, but I gave you in the midterms questions an example so that you can see how they can be integrated. And here, this is just so that dissolved pollutants are degraded. So this is independent question related to settling. So you have a mass balance equations and you solve it. So the midterm question was much more complex than these questions. But to be fair, in the last year, I gave them also the similar example questions before midterm so that they go through this process of understanding it. I didn't want them to do it just out of blue. This is already we cover. This is the concept of uh, this is the concept of um, the precipitations where just you can calculate or you can decide. There was a quiz question on that. You should see that. But any question like this, is a short question, 2-point questions. These are not 5 or 10-point question. It could be just a simple question like this, and you'll just calculate that value. So understand each steps, okay? Because the short question in midterms exams are quantitative too, not always qualitative. And here, just know the concept. Why? What is PE? This is what does that means even? Effective precipitations. Why effective precipitation is less than real precipitations? Effective precipitation is basically the fraction of precipitation that become runoff, because all the precipitation has not ended up becoming runoff. So this concept is important for you to understand. For instance, you can see that here, large lot residential, the corp number is 77. If you go to open space, the corp number becomes 74. If you go to gravel road, the corp number become 89. So they are changing for a reason. So you got to understand what's the reason. Basically, the more impervious surface, more runoff, more the corp number. Okay, because it doesn't have any place to retain, or retention is low. So that's the whole equation, sir. These are just empirical terms. You put those value and get those answers. Hydrograph, as I said, I will not ask question on unit hydrograph, even though I love to, but because this is something important for your understanding of water quantity quantifications. But I'll give you another extra homework, which is not, will not due, but it's just you have to do it for practice. So that you learn this process, because every consulting project you go, you will do this unit hydrograph using a software. So you should know how the software does. So this is a very important question for hydrograph means how much storm water you are going to receive in that locations. You got to have that number. But you got to understand what is this peak means, what is the peak, lag time, all that factors. Those are the things will be in the midterms. What is time of concentrations? What is lag time? How to calculate it? All those numbers has meaning. Okay.
Professor, do you
Yeah.
mind going back up to the question that had steady state again, where C equals C out? Yeah,
Here.
that's one. Yeah. I was just curious because for this one, it seems like the concentration is steady state. So like C in equals C out. Is that true or no?
No. So the C in equal to C out. Let's put it this way. What is steady state means is that concentrations at any location, space, is going to be constant. You are not measuring, you are not comparing concentration at two different points. You are comparing the concentration at same location at different time. Okay. So steady state means that concentration at that location always going to be same number. Okay. So
Okay.
so if you when you go back, comparing effluent versus influent, they're not the same because they are two different locations. They could change because something might react inside, right? But even despite reaction, all the time the concentration in the effluent will be same 10 minutes ago, 2 days after, whatever time.
Okay. So like the only things that we could do for steady state would be like Q in equals Q out,
Yeah,
and then mass in equals mass out,
mass out. Yes.
but not C in equals C out.
No.
Okay. Okay, that makes sense.
Concentration is not conservative. Mass is conservative. So
Okay.
when you say flow Q in equal to Q out, those are actually mass, like a mass of water. Because density is constant, so that's why volume, because flow is volume, right? Volume equal to mass because you assume density constant. So that's the mass conservations.
So even if there is like decay of if let's say there's no decay of concentration, then it's still, you still can't do Cn equals Ci.
Let's think an example, right?
Okay.
So you have a pond, there is no decay, and you are adding contaminant in, and there is no decay, and there is nothing going on, and the effluent is going out, and I say steady state, right? So then at that point, actually C in equal to going to be C out. The reason is when you solve it, you will find that out. Because if you see this equation here, okay, there is no reaction. So the K equal to 0, right? So what it becomes? C in Q minus C out Q equal to 0. So that means C in equal to C out. That's the byproduct of that because there is no reaction happening inside. So where they go, everything that going in has to go out, right?
Yeah, that makes sense. Okay. Okay, yeah, thank you.
Yeah. Okay, so what about, let me see, that's the homework number 3. Let's go to homework 2.
I just had a quick question, Professor.
Yeah.
Is a green roof just a biofilter that has been placed on a roof? Or is there something different between like how you would design a biofilter versus how you would design a green roof?
So that functionally is the same. Okay, there is a filter on the top of roof. The how you design is going to be different because you don't want too much wet. You don't have a groundwater there. So what kind of materials you're going to add? Because you don't want to store that water there too long. Okay, at the same time, you also don't want to drain them too quickly because the green roof require more water. Okay. Um,
Okay, thank you.
But we'll learn that in the class, right? But the same process. It's a filter material on the roof. Things move. It remove pollutants. But the challenge is not the challenge. In unlike biofilter, which is on the ground, you have a lot of polluted stormwater. But green roof, where the pollution will come, it's atmospheric dust. So we are not really concerned too much about the pollution. You are more about whatever the rainfall happens. You just want to filter it and keeps the soil or the roof cooler than before, and just have a extra space for farming.
I think I was just doing the practice midterm and I was got to, it was like in the short answer questions asking about, what design changes you could make to, increase or decrease how much like irrigation you would need for a green
Oh,
roof.
so, okay. Sorry, that don't even bother those because we didn't really cover green roof. Last year we covered
Okay.
green roofs. That's why we asked this question.
Gotcha. Okay. Yeah, I was, okay, that makes sense. Thank you.
Yeah. So if you didn't, so we cover so what is that permeable pavements, but we didn't really put that as part of the midterms, right? So anything permeable pavements after is not part of midterms. It's before that. So week up to week 11, which is bioretention system.
Okay, perfect. Thank you.
Yeah, last year I was recording 50% of the class and in person 50%. What ended up happening is when I record 50%, that's basically I record a lot of materials. So I ended up putting a lot more materials per class. So we finish very quickly. But then it's also not good because you're exhausted because you're watching so much video. So I change that. I say, okay, whatever pace is going to go, that's how it is going to go. So that's why we didn't cover more materials by the time this time.
I'm sorry, this might be a dumb question, but I still am not getting the concentration thing. So like if you had like a pond and there's no decay of the contaminant and you have an inflow of the contaminant at like 10 milligrams per liter concentration, and there's no contaminant in the pond, wouldn't the concentration out still be different because the concentration was diluted by the pond's water?
You're right. You're right. So that
Okay.
would be different at the beginning, right? So with time, the original water from the pond will slowly decrease. You'll repelling with the contaminated water. After a point, steady state means it's gone for infinite time, long time enough to make a difference.
Okay, so like in steady state, because it's like considering infinite time,
Yeah.
C in will still equal C out
C
if
out.
there's no decay.
Yes.
Okay.
So another way to say is, if you solve this question, let's go back to this question. So let me solve that right away so that because that's a very good concept question. So let me share the slide. So another, the better question to ask or the right question to ask is, how long before, let's say you start injecting a contaminated water into a pond which has no pollutant before, how long before it becomes completely same as, how long it before the effluent concentration um, same as influent, how long it takes, because at infinity everything will be same because steady state, or how long it will take before to achieve the steady state. Okay, so if you do that one, let's write this equation, create a questions, that way you guys see the screen. Okay, all right, so I'm creating a hypothetical question. So this is a pond as a volume V, okay, K, no reactions, pollutant doesn't degrade inside it, and you have effluent going in, influent coming in, right, and a flow rate of Q. Initially, the concentration is 0 inside, so Ct equal to 0 is 0, okay, and now you start suddenly adding a polluted stream, okay, or suddenly adding a contaminated stream, which become C naught, okay, that's the thing coming in, or C in, let's say write C in. So now question is, how long before if you want to plot how the concentration C out as a function of time, okay, how that is going to change, because initially it will be 0, right, because nothing is shows up yet. So initially there are nothing there, so initially C at t equal to 0, t equal to 0, C out 0. Okay, the question is how long it will be before it's seen, or another says after how many days what concentration will be, right? So you can, another question you ask is at t equal to, let's say 5 days, what is C out? Okay, so this is a very typical question where a spill occur, where suddenly somebody discharging polluted water, and you want to know how long before you start seeing the effect. Okay, so that's the unsteady state. The moment I ask how long, what's the concentration at different time, that's unsteady because you are talking about time. Things are changing at that spot. As I said, unsteady means concentration change at that spot with time. Okay, so let's solve this equation. So again, um, what I'll do is I'll just write the mass balance equation. So Q, C in, C out, and let's say this is a completely mixed system. So C equal to C out. Okay, and K equal to 0 because no degradations, and volume of, this is the volume of pond. Okay, so if you write the equation, so this is not steady state, right? So that's why you can write volume dc by dt of system, which is pond, is everything that coming in, right? So that's going to be concentration times C in. Then what's leaving the system is Q times C out. Is there any reactions? There's no reaction. That's why you can say that this is all 0. Okay, so no reactions. So because it's a complete mixed system, you can assume that C out is same as C in the pond. Okay. So if you write this one, so that will be B dC by dt equal to QC in minus QC. Okay, so that become, now you have to solve for this C with time. So again, this is the exact question we solved in the example or homework. I forgot because this is a differential equations where first order differential equations. The two way to solve is you put this as a different variable. So let's say C in minus C equal to C dash. So that means this C, if you take derivative of both sides, d by dt, C in minus C should be dC prime by dt. And the left side will be C in is a constant, so that the derivative is 0. It doesn't change. C in is a constant. So it's going to be minus dC by dt is same as dC prime by dt. So if you put this value here, this question become dC prime by dt is equal to Q. This one is C prime. Now you can solve this one because it's now you can integrate it. So that would be dC prime by C prime is Q by V dt. Okay, and let's say C prime initial as t equal to 0 and t equal to some time t, and then the C prime t equal to 0, C prime t equal to t, whatever that value is. Okay, so if you solve this one, that basically is log C prime at t equal to 0, C prime at t equal to t, whatever that value is basically Q by V t. Okay, so so let's say at t equal to 0, C equal to 0 because there is nothing in the effluent, right? That means C prime, which is C in minus C, should be C in because C equal to 0. So that means T equal to T, C equal to CT, whatever that value is, because that's what you're solving for, right? In that case, C prime will be C in minus CT. Okay, so if you put this value here, ln C So what you can do is you can ln C prime at Ct equal to 0. This is C in, and this is C in minus Ct. So if you put this one, that means ln C in minus Ct okay. And if you take the logarithm, so this is basically log a minus log b is same as log a by b. So if you put that value here, that's log ln C in minus Ct divided by C in is Q by V T. So if you take the exponential both sides, so this is basically C in minus Ct by C in is exponential Q by Vt. So if you put this value, this will be basically 1 minus Ct by C in. So if you solve for this one, basically if you take both sides, so this is Ct equal to C in 1 minus okay. So if you cross check it, let's say at t equal to 0. So when you put at t equal to 0, what this value would be. So you can see this to 0. So this is basically exponential e to the power 0 is 1, right? So 1 minus 1. Oh no, e to the 0 or something. I have to check. So you can put this number and you can see what the value would be. I think it should be, yeah, it should be 1. So if it 1 equal to 1, so 1 minus 1 equal to 0. So that means initially Ct equal to 0. That's how it should be. And so that means if you plot this value, that's how it is going to go. So it's it will start with 0, but it'll go all the way. So let's say t equal to infinite. So this will be something like, I have to see whether there, maybe I make a mistake in numbers or the minus negative sign somewhere, but this is the whole concept. Okay, so initially it will be 0, but an infinite equal to infinite, it's become like C in.
Okay, thank you.
Okay, any more question?
I think I'm good. Thank you so much for the office hour, Professor.
Great, great. Good luck for tomorrow.
All right, thank you so much. Have a good day.
You too.
Bye.
I had one quick question. On the practice midterm 1B, when I just went through and did it myself, I used like Darcy's law to solve it, but then there was a different equation used in the solutions. I was just a little bit confused about the equation that they had. But I got the same answer, so I wasn't sure if like the way I did it was fine or what.
No, it should be fine. The equation that's used is basically I just break into multiple. It just if you keep putting every terms, then the final form will be this. It's not. You mean this one?
It was 1B.
Oh, I'm sorry, 1B. Which one? This one?
No, up a little bit more still. A little bit more. Yeah, this. Oh, wait. Wait, I think it's on like one of the first couple of pages of the document. It's like on page 3.
Here?
Yeah, this K equal to L over T, ln H initial over H final.
Okay. So this
I just hadn't seen.
Oh, I
before.
see. So what is this? Okay, so this is the falling head test for hydraulic conductivity.
Okay.
Did we do this one in the class? I forgot. But if we don't do it, don't worry. But if we did it, it's just a. This is basically how to measure hydraulic conductivity in a lab. There is a equation.
Okay. I remember us talking about that conceptually, so maybe I'll go back in the notes and see if we covered that equation and I just don't remember it.
Let's see. I can find out right away. So implications number 2, mass balance process. Infiltration rainfall, hydrology, infiltration rainfall annotated. One of unit hydrographs. Okay, stormwater hydraulic. So maybe this is the one. Okay, let's see. No, not that one. Yeah, so sometimes I may not have covered. If it is not, it's not. But if it is there, that's just the. I don't think hydrograph will have that one. Okay, physical process. Maybe that's where it will be because this is a physical process. Let's see this one. Okay, it is here. You are muted, Madeline.
Sorry. I'll go back over this lecture. I must have just
Okay.
forgotten about it.
Yeah, there are
Okay.
two kind of tests, falling head, constant head. Just sometimes
Okay.
that it might be a right thing, but I change it. Just check the
Mhm.
solution in the book or the things that.
Okay. Awesome.
Because what we do is normally students make mistake in which one is initial, final, where it should be. Okay, that negative sign. So that ended up getting a negative K. If you're getting a negative K, very likely you have made the mistakes in the sign somewhere.
Gotcha. Okay. Thank you.
Okay, any other questions?
I had a question for homework 3, question number 1.
Okay, question number 1. Okay.
I got a very different answer because I converted my Q to meters cubed per second. And I was wondering why the solutions doesn't do that.
It should not, because the unit has to cancel out. So check that one just in case there are some issues there. But I'll tell you one thing, in the exam, you write all the process correct, you get the full point. Okay, so write the units, because most likely where things can go wrong is the unit conversion. So for instance, G equal to the G acceleration due to gravity is meter per second square, and your rest of the terms are not in meters. That's where you make mistakes. So those are genuinely, you lose some points there because that you didn't recognize the units are not matching. But if you write the units everything same way and change to similar units so that they cancel out, you'll get full credits irrespective of what your answer is.
Like I was wondering why for Q the units are in meters cubed per hour, but VS is in meters per second.
No, it should not be. It should cancel out. So there has to be same unit. I didn't check this one. So this is TA did. I have to check. I'll check if there's some issues there. So everything. Long story short, this has to be second. If it is hour somewhere, it should not match. Okay, the hour has to be converted to second.
Okay, thank you.
I had a question about the final project, but if Annabelle, you have any other questions, do you want to go?
No, you can go ahead.
Okay. So I am designing a bioswale for our project, and so I found like certain equations online for how to design a bioswale, and it mentions Q subscript WQF. And I was wondering what that means. I read somewhere it was like water quality flow, but I was wondering how that's different from just regular flow.
So water quality flow means the amount of flow that is going to be treated. Because just because you get a lot of flow doesn't mean that all of them will be treated. So water quality flow is the fraction of flow that actually going to be treated or retained or go through the treatments.
Okay, thank you.
Okay, we are right at time. If you have any question, I'm here for now. I keep it for 3 hours, 2 hours. But let me know. You guys can discuss anything really. It doesn't have to be midterms, whatever you. But what we can do is I can stop the recording. That way it doesn't just have a lot of pause moment. Because let me do one thing because already 1 hour. So I'm going to stop the shares and stop the recording.